Thank you, Denkin. So first of all, thank you for the invitation. Thanks to all the organizers for putting together this wonderful workshop. It's a great pleasure to be here to speak right after Patrick Perez as well. I think it's a great list of speakers that you have, and just the number of people in the audience shows that you're really attracting a lot of interest. I think the topic is important, computer vision for all seasons, and this is indeed something that we're looking at in the context of visual SLAM.
Thank you for your support.
Yeah, so the work that I'm going to present has been done mostly by current and former team members of mine, in particular Nan, Lucas, Patrick, Niklas, Roy, Jacob, and Felix. It's about visual SLAM, as I said. Let's see how I can get the starts to work. There's 4 parts. The first part is a more classical direct visual SLAM methods, then deep, how to make these deep, how to enhance them with deep networks, how to also use deep networks to create dense, large-scale reconstructions from a monocular camera. And lastly, I'll focus on the key topic in this workshop, namely how to make deep SLAM for all seasons. And this is predominantly talking about developing the right data sets for making that happen. But let's start at the beginning. The beginning is, in this case, long time ago. So this is one of the pioneers in you could say computer vision, who worked well before the advent of computers, Erwin Krupa, in fact, in 1913, so more than 100 years ago, he proved this classical result that if you observe 5 corresponding points in 2 images, you can recover the relative motion of the camera and the 3D structure of these points, right? And this is definitely a breakthrough result that the vision community started building up on in the 70s, 80s, 90s, and around the 2000s, some of the first real-time capable structure from motion algorithms were presented. Nowadays, it's often called visual SLAM, essentially same thing. I think one of the first ones was in Stefano Soato's team around 2000. And this is just a small selection of the pioneering works in visual SLAM. Most of these actually do follow in the footsteps of Krupa. So they start with 2 images. They extract points because Krupa said we need points. And then they identify corresponding point pairs, typically using descriptors like SIFT, SURF, brief, etc. And then once they have pairs of corresponding points, they run basically algorithms that build up on Krupa's results, bundle adjustment in particular, to recover camera motion and 3D structure. And what we've been promoting over the last, say, decade or so are so-called direct SLAM methods. The idea is that you deviate from this classical, say, key point-based approach in that you don't do that intermediate abstraction step of point extraction correspondence estimation, but you do it all in one go. So you directly go from your raw sensory data, the brightness values of your camera, to a reconstruction of 3D motion and 3D structure and camera motion. And the idea being that, you say find a camera motion such that, and a 3D structure such that if I project these colors into the world and back out, I should get color consistency. And so, in fact, the key difference here is that the reconstruction of motion and structure is done not in the classical way by bundle adjustment, where you minimize a geometric reprojection error, but instead we minimize a color consistency error, a photometric loss function. And this is really the difference, that the photometric loss drives everything. And so since you don't have that abstraction step, there's less of a risk to make errors in the correspondence estimation that you may not be able to recover from later on, right? Because it's all done in one step. One of the first approaches in this line was a technique that we called LSD SLAM, for large-scale direct SLAM. It turned out to become quite popular over the last couple of years. This is an overview of the method. It's somewhat involved, one should say. The input video comes in on the top left at, say, 30 frames a second. And then there's 2 alternating threads that are run on 2 cores of a CPU. One is tracking the camera, and one is generating depth maps, key frame-based depth maps that are then merged into a large-scale reconstruction. But here, just to glimpse into why is it called direct. The camera motion is estimated with a loss function that is essentially minimizing, as I said, brightness consistency. So you have a keyframe, you have the current frame, you try to warp the two frames in terms of their brightness values. So for all pixels X, you want the brightnesses to coincide. Here, U is the inverse depth, and G psi is the rigid body motion of the camera with 6 parameters, modeling, translation, and rotation. Since it's only 6 parameters, this can easily be done in a coarse-to-fine manner, even on a single core of a CPU. This runs in real time. And so on the other core, you can then do depth map prediction. And as a result, you get a method that runs in real time on a laptop CPU. And it maps, as you can see, the 3D world and tracks your camera in real time. And it is large scale capable in the sense that beyond what was then possible among real-time capable SLAM methods, it doesn't only recover, say, a desktop environment, but you can really take it outdoor. And as you can see, recover fairly large environments with essentially no or very little drift. And in fact, that was then the key challenge that's been bugging us for the last years, is how to further reduce the drift. What you see here is the next generation. After LSD SLAM, Jacob Engel developed direct sparse odometry, a follow-up work. There's many differences, but the key difference is in DSO, camera motion and 3D structure are really estimated jointly. So not alternatingly in two separate threads, but by minimizing one joint loss function with a Gauss-Newton type optimization scheme. And the way to get this to real time, the key aspect was to do it in a sliding window fashion. So we jointly estimate the camera motion for a set of consecutive keyframes. That way we get a good compromise between real-time capability, but still getting fairly large scale consistency. Still, there is a drift if you take this too far, as in this example, through the subway station back out on the other side. You see the bicycle that you see on the top left is recovered twice. There is a drift of, say, 2 or 3 meters on a distance, though, of hundreds of meters of traveling. Just one camera, right? So we wanted to quantify what is the drift. And this is not easy. We want it to work in the real world. So we took a lot of real world data with different lenses in different environments, different motion patterns, some more translation, more rotation, some faster motion, etc. Lots and lots of sequences. And then for each sequence, we don't actually know where the camera was halfway through the sequence, but we do know where it should be at the very end, because they all loop back to where they started from. And so we can measure for each sequence the total drift in translation, in rotation, and in scale. And we plot here the drifts on the x-axis, on the y-axis, the number of sequences where we achieved a certain drift. And ideally, you want to be obviously in the top left corner of these plots, meaning for as many sequences as possible, you want to have a smaller drift as possible, right? And this is a comparison to what we consider the state of the art in real-time visual SLAM, a powerful technique called Orb SLAM from a team in Zaragoza. But still, you can see, compared to Orb SLAM, we get a drastic improvement in both precision and robustness. If you say the best 300 sequences, what's the total drift in translation? Orb SLAM has a drift of 6. We have a drift of 1. Right? So it's almost an order of magnitude less drift. Or if you say you want a maximum drift of 2, how many of the 500 sequences can you track? Orb SLAM can track 100. We can track 400 out of the 500 with that drift. So there is a significant boost kind of also in robustness, if you will. So that led us to create this startup called Artisans, which currently has around 25 employees working on a number of topics. The idea is to actually bring these SLAM technologies into the world, into the market, into autonomous systems, into robots, cars, and drones, and whatnot, right? Artisans is focused on 2 aspects. First of all, sensor development, so the development of stereo inertial sensors, often fused with RTK, GPS, and whatever other sensory measurements you might have. And then spatial AI algorithms to process this data. And we found that the sensor development is important because typically this off-the-shelf sensors often do not offer the right quality in terms of calibration, synchronization, timestamping, and all So this is why sensor development has always been part of the Artisans tech stack. Here's the first work that was done in conjunction with Artisans. This is an extension of DSO to stereo cameras. And once you have two cameras, that first of all gives you the scale of the world because you have a baseline, so you have metric scale. And secondly, you see the drift is even smaller. We can really drive around the block with a stereo camera rig and we get almost no drift. And so we can now start to map large environments with hardly any drift, as you can see here. And all of this is done in real time. We often demo this. There's tons of videos on YouTube, so I'm going to, for time reasons, skip and move on. Here's another video. I'm not sure that's on YouTube yet. This is work where Artisans deploy deep networks to create semantic maps. The idea being that you can semantically label not images like is commonly done, but semantically label the 3D world to distinguish which areas in the world are drivable, which are sidewalks, pedestrians, etc. You see, it's very large-scale maps. In fact, we drove 8,000 kilometers of coverage in a whole fleet of cars equipped with these sensors, and so in a matter of no time, we mapped a large part of Berlin to demonstrate this capability. And I think this is a very important capability to create semantic maps, because you want to know what the world is that you're driving through, right? Is this pedestrians? Is this cyclists? Is it cars or buildings, etc.? Next, I want to talk about how to use the predictive power of deep networks to actually improve SLAM. So not just extract semantics like you saw here, but really actually improve the SLAM itself. And this has been an endeavor that people started a little bit later in the deep learning community, maybe because it's a bit more challenging to learn things about the 3D world, the camera motion, etc., etc. This is a few representative works that started emerging around 2017, but they all have one thing in common. They all show that you can tackle this challenge with deep learning, but they all do not exhibit state-of-the-art performance when it comes to visual odometry on established benchmarks. And so what we advocated is a hybrid technique that is not fully end-to-end learned, but ideally combines the best of both worlds. The classical SLAM approaches, the energy minimization techniques that have all this knowledge about perspective projection, about pose graph optimization, things like that, but then combine these with the predictive power of deep networks. And here's how we advocate to do it. Turns out you can train a network to predict from just one single image. This is work by Kuznetsov and collaborators, very beautiful work where they do monocular depth prediction. And by now there's a whole zoo of deep networks, mono depths and others that do this kind of depth prediction. At the time, 2018, we built up on this network. We developed a new architecture that we call StackNet that, as you can see, gives significantly crisper depth predictions here. And now you can take these depth predictions and feed them into a SLAM approach. Ideally saying, find a reconstruction that is for every keyframe consistent with the deep network prediction. And what you get is a monocular SLAM approach. We call it deep virtual stereo odometry. In retrospect, I think this was not a good choice of name, because the community always thinks it's a stereo method. It is actually a monocular method. So from one single camera, you can see, whereas the baseline has a significant drift, we have almost no drift in this monocular approach. And it actually gives you scaled metric reconstructions. You know, I've been telling my students for generations that you cannot get the scale of the world from a single moving camera. Turns out I was lying. You can if you know the world that you drive through. And the network can learn the depths in metric units, right? And so we can compare this monocular approach to some of the state-of-the-art stereo approaches here, stereo LSD SLAM, stereo ORB SLAM, stereo DSO. And the solid numbers are the best performance. This monocular method actually outperforms these top stereo methods, right? So this is quite impressive to see that this predictive power of the deep networks allows to compensate for missing sensory information. In fact, we can go further. We can not only predict the depths, but we can also predict camera motion and uncertainty. This is Nan Yang, who in his follow-up work here then showed that all of these can be fused into a SLAM approach. To be more specific, from a single image, as I showed you, you can predict depths. Once you have two consecutive keyframes, you can predict the relative camera motion between the frames, and then you can warp the two frames and introduce a loss function for training the network that just imposes brightness consistency, right? Which means we don't even need any ground truth for depths or camera motion. All we need is the video sequence, right? And we can train it in a fully self-supervised manner in this way. Unfortunately, once you do that with real imagery, cameras are typically not brightness consistent. Even if they teach you that in computer vision 101, take a real camera and that aperture changes, the brightness changes quite significantly, actually. But we can train a deep network to correct for this brightness variation, to introduce an affine brightness correction with parameters A and B here, and thereby align the two images, not just in terms of the rigid body motion of the camera, but also in terms of the brightness. And that works here in the indoor kind of Lambertian world, right? But if you try to take this outdoor, you'll find that in the outdoor world, there's many areas in the image where brightness is not preserved, because it may be glass, metallic, all these non-Lambertian structures, or maybe in the trees when they move around and they have an ego motion, then from frame to frame, the brightness will not be preserved. Turns out for all of these phenomena, we can simply, these are complex phenomena that are very hard to model explicitly in a classical fashion, but in a deep learning setting, we can just train a network to predict what's called an aleatoric uncertainty. And then we can simply downweight the residual based on this uncertainty, saying, tell me which areas of the image are likely not to have brightness preserved. And then I'll simply downscale those in the whole total residuum. And then I can now train this in a self-supervised fashion to predict all these quantities. And then I can feed again these quantities into the SLAM approach. For time reasons, I'll not go into technicalities, but we feed them into both the front-end tracking in terms of a nonlinear factor graph and in the back-end optimization, essentially adding terms to our classical SLAM loss that say the depth predictions should be consistent with what the deep network predicts, right? And then all of this can be optimized, and then we get very accurate depths in particular, but also odometry. So let's look at depths first. This is a comparison both on Kitty and UROC with one of the state-of-the-art methods called monodepths 2. And you can see we get a significant improvement in depth prediction by D3VO. And then it turns out this also generalizes nicely to other data sets. So even though we trained on Kitty, the depth predictions and uncertainty predictions on cityscapes are very, let's say, plausible here, right? Next, we can look at visual odometry, and again we find that the deep network compensates for missing sensory data, right? So we compare here to both mono and stereo methods, both classical and hybrid methods, and you see a significant again boost in precision of the visual odometry. In fact, we can even go further and compare to visual inertial or stereo inertial methods, and we see that this monocular method D3VO is on par with the state-of-the-art stereo inertial method called Basalt. Right, and this I find is quite impressive how precisely you can track a single camera with this approach. Since we can track a camera in real time with this monocular approach, we can go further, and this is work that was presented at this week's CVPR. We can try to predict dense worlds from a single moving camera, and or generate, I should say. Predict is maybe not always the right term here. We use a deep network for this. The deep network has three components: a cost component, a mask module, and a depth module. The cost volume component basically takes not a single image, but a sequence of frames and creates a cost volume, and then uses color consistency in the cost volume to predict depths. In addition, there is this mask module that is trained to filter out moving objects. And how does that work? Well, essentially based on color inconsistency, right? Everything where after warping with their ego motion, the colors are not consistent is likely a moving object. And so we can train a network to estimate the moving objects and remove these so as to filter out any unwanted moving objects. So the videos we take as input, they have cars driving around, but the reconstructions like the one you see here, they just show the static part of the world. And in more experiments in the paper, we show comparisons where you see the difference, how the moving objects are really eliminated from the reconstruction. But what I like in particular about these reconstructions, it's a bit jerky here. I think this must be the video connection. But what I like about it is that you can really see nice dense worlds created from just one single moving camera. You know, no stereo, no GPS, no inertial, nothing. Just a single drive through a single camera. We get very detailed and plausible dense reconstructions that can essentially rival in many ways with LiDAR point clouds, right? And for example, in terms of point density, this is significantly higher than what LiDARs typically give you, right? And so this is again one argument that in my constant storyline that I think on the long run in autonomous driving, the camera will replace the LiDAR sooner or later. It's cheaper, it's more lightweight, and it gives you much more density of information, and you can extract semantics, etc., etc. So it will definitely become the lead sensor. Now, when you talk about cameras, though, in this field, people always say, but cameras don't work in the night. That is actually not true, right? I don't know where this rumor comes from, right? But they do work in the night. I mean, our eyes work in the night, right? So if the eyes work in the night, cameras should be able to do it. Maybe there's an aspect of high dynamic range that could be refined, etc. Obviously, you have to switch on the headlights to illuminate the world. But then I think we can even make them work at night. The key challenge, though, is you need to develop the data sets to enable the community to actually look into this and to kind of fine tune algorithms so that they do work at night. And so this is what we set out to do here. This is images, I think, from the Oxford Robocar dataset, where you often have the same environment, but in different illumination, in different weather, right? For example, snow and not snow here on the right and left. And what we wanted to do is to focus on relocalization. And this is a work by Lukas von Stumberg and collaborators called Gauss-Newton net. I don't want to go too much into technicalities about this work, but the key idea is the following. Assume you have mapped the world like I've shown you in one illumination condition, driving through it, say in summer or in winter, whatever. And then you come back to the same environment at a different season, at a different time of day, different illumination, different lighting, different weather, different, season, etc. You want to relocalize yourself in the previously created map. And this is what the Gauss-Newton net was designed to do. I don't, again, want to go into the technicalities of how this network works, but essentially you have images and you try to find the closest images in the database that were possibly taken in different weather. And you see the blue point cloud is the newly created point cloud. And as you can see, it aligns very nicely with the previously created point cloud. You can see here the parked cars in blue were not there at the first time of mapping. They get added to the map later, so we can actually enhance a previously created map because we're able to relocalize ourselves in that previous map. Again, there's lots more videos. For time reasons, I'll have to move on here. I refer you to the web for the videos. What we developed as part of this work is a let's say small data set that we compiled both from Carla and from Oxford Robotcar. The Carla, it contains 9 training, validation, and test sequences. In the Oxford Robotcar, there's 2 training sequences and 6 test sequences where we want to evaluate the precision in terms of relocalization, right? And so this is again similar plots as before. On the right axis, on the x-axis is the relocalization translational error. On the y-axis, the percentage of relocalizations where we've achieved a particular error, right? And again, you want to be in the top left, and not surprisingly, we are. I mean, that's the usual story in all of these presentations, obviously. But what's more is we can actually, one of the things we showed is that this method generalizes very nicely, even though in the training there was no snow, it even generalizes to map between sunny and snowy conditions. So there's something the network learns that generalizes across the seasons. But we decided there is need for a larger data set. You know, if you look at the popular data sets, Kitty is all in one weather condition, essentially sunny blue sky, right? Diverse environments, but same weather condition. Oxford has diverse seasonal conditions, but always the same drive, right? So we wanted a diversity in the environments, in the drives, lots of different drives, but we wanted to, you know, drive all of these multiple times so that we can see them in different weather, in different seasons, spring, winter. You see on the bottom with snow, on the top right you have rainfall, on the bottom right you have examples of night scenes, right? And this is important because, as I said, night is a particularly important topic to I think focus on for the vision community. There's large-scale maps, maybe a few words, centimeter accurate georeferenced 6 degrees of freedom pose, and in addition, accurate pixel-wise correspondence so that you can, you know, quantify, you know, relocalization and things like that. How did we record all of this? This is the Artisans car, and what you see on the roof here is a sensory system that includes a stereo inertial sensor and an RTK GNSS receiver, properly synchronized, calibrated, etc., time-stamped. We drove over 350 kilometers of recordings, so quite abundant data. There's 9 different scenarios in this data set. We have multiple traversals of a certain scenario so that you can check if you can, you know, relocalize across weather. There's changes in seasons, in lighting, and in weather. Here's an example of the trajectory, and as you can see, we can even close up, create close-ups to see it's quite precise. How did we generate this ground truth here? We ran direct stereo inertial odometry. We fused it with RTK GNSS information to offer global coordinates and to remove drift. And in addition, we did loop closuring and pose graph optimization. Let me show you the last component is not unimportant, especially in environments where you have very little GPS or RTK GPS. Here, for example, we drive into a parking garage, and as you can see, we loop around many times in the parking garage, and by the time we come back out, there's a drift. And then if you don't have a GNSS measurement at that point, the drift will not be removed. But once you do pose graph optimization, you can actually, as you can see, correct for this drift. In fact, here's a kind of a more perspective view where you see we drove in this parking lot on multiple floors before we basically came back out. So it was quite a long drive indoor. But I think this is important, right? These are the settings where GPS will not be there, right? And we're just assuming that you have a GPS that tells you where you are is not going to work, right? And this is exactly the setting that Artisans has been focusing on for the last few years, how to offer localization, highly precise localization in GPS-denied environments. Here's more. As I said, there is point correspondence across, you know, different lighting, across different weather, very pixel accurate point correspondence that comes along with this data set. So I offer you to test it out. It's called the 4 Seasons data set. So I hope I didn't go too fast, and I hope I'm still roughly in time. I talked about LSD SLAM and about direct sparse odometry as two of the leading examples in direct visual SLAM for real-time large-scale mapping. I showed how you can extend these to stereo. I showed how you can enhance them with deep neural networks to get more precision and more robustness. I showed that you can use deep networks even for semantic mapping of large-scale environments. And lastly, not lastly, but I also showed how you can train deep networks to create dense, large-scale maps of the world from just one moving camera. And then all the 4 seasons data set, all this that we hope will inspire the vision community to tackle real world outdoor large scale mapping and localization across the seasons. Thank you.
Yeah, thank you, Daniel, for the really excellent presentation. It's very nice to see that you are able to put so many great works in a 30-minute talk. So yeah.
Sorry, I may have gone a bit fast today. I usually speak slowly, so I try to
Are there
compensate.
any questions that about some part of the talk, or like, yeah? You can unmute yourself, ask question directly, or you can type your question in the
I
chat.
prefer that you unmute and speak, even, maybe even with camera if you can, because that
Yeah,
makes
that
it
would
more
be great.
entertaining.
Before we have questions from the audience, perhaps I might have a question for Daniel. So we have these static worlds that are reconstructed, right? All the buildings, trees, perhaps parked cars. But I'm wondering how we can also add some life, some dynamic, content there, because it seems like all like very static, not very lively, let's say. So of course it's a broader question. It's not like perhaps for.
So I think this is an important question. I think there's many facets to this question. The first thing is, for example, in the last work on the bottom right here, a monorec we called it. This is a technique that deals with dynamic worlds in the sense that it filters out the moving objects, right? And what remains as a reconstruction is, let's say, the static background, if you will. I think this is useful because it's a background that you can then use to train self-driving cars, for example, right? Often you want environments to train them in, and you don't want them to put the self-driving car in the real world because it creates lots of damage and accidents. You can train it in a simulation, but the benefit here is that you have a synthetic world that is a copy of the real world, and it's created as such. So it has all the properties of the real world in terms of the geometry, the objects, the colors, all of that, right? But your question is a good one. How can I actually reconstruct the dynamic world? Not filter out the moving objects, but this is indeed the next step on our agenda, is to start modeling the moving objects. And there's many facets to it. You can start by modeling rigid motion objects, but then you can also have non-rigidly moving objects. But in the end, if you think about this longer, basically all of computer vision comes, back at you here, non-rigid motion estimation, multi-body tracking, structure for motion for non-rigidly deforming objects, learning shape and 3D structure. There's a lot of challenges that all come together here, and so it's an important challenge, but it's not an easy challenge. So we're going at it, let's say, step by step.
Thank you very much.
Yes. So regarding this moving object, maybe I actually asking a following up question. This moving object, there are two corner cases. I was wondering, how do you handle this? One is the moving object which moves at the same speed as the ego vehicle. Another one, if there's like big moving object, then you have rather homogeneous surface, like a truck, for instance. Then even if it moves, then when you compare the color consistency, it's still quite consistent for large area, right? Overlapping area. How do you handle this two type of moving
So these are two different corner cases that are both challenging. The second one is the classical one. If you have no texture in the world, then vision-based techniques, are let's say challenged. And the first one is the fact that the object completely covers your view, and it may be moving as well. And indeed, this is one of the nastiest corner cases for us at Artisans. Artisans has put a huge effort into exactly eliminating all corner cases to assure performance across not just seasons, but very different scenarios, right? And the biggest challenge on that roadmap was, in fact, if we stand right behind a truck and the truck starts moving, then our SLAM system often thinks it's moving backwards, right? Issue is you can deal with that in many ways. The first way is that you can fuse with other sensory information. You can fuse it with GPS, RDK GPS, to tell you I'm not moving backwards, right? You can fuse it with IMU information, inertial information, and you can fuse it with wheel odometry to stabilize, right? So whatever sensors you have on the car, obviously you should tap into these and to get a kind of a maximum consensus on what is the motion, right? And that way you can rule out some of these corner cases. And another is that you can expand the view by tapping into more cameras, sideways, backward facing cameras. And that actually also eliminates the structureless challenge. Unless obviously your car is in a completely white bubble surrounded and in all directions it's just white. But when is that ever going to happen, right?
Okay,
So,
yeah.
So I think you can eliminate all of these corner cases by just tapping into more sensors.
Yeah, definitely. Yeah, there are some questions. I think the shorter one we can read, and the longer one probably is also like easier if you can ask directly, because if you read then probably it's very hard to follow. The shorter question is like from Harish, is actually why you use the monochrome camera instead of RGB camera when you collect this 4-season data set.
That's a good question, indeed. One of the reasons, and I think the main, so I'm not a hardware expert, I should say, and that there were lots of design choices that we made in the sensory system. Often, for example, if you move to color cameras, you have these Bayer patterns to deal with, and so a lot of the photometric issues get a little bit nasty and involved. But another aspect that I think is also very important is we consistently found, both in our work on optical flow, but also in our work on visual SLAM, that color doesn't really improve the performance in terms of mapping and localization. Obviously, color is helpful if you want to detect the stop sign. Yeah, no doubt. The fact that it's red does help. but I think for the geometric understanding of the world, the reconstruction and the mapping and localization, color doesn't give you a great benefit. Why that is, I don't know. But even in optical flow, we never found, even back 10, 15 years ago when we developed lots of optical flow methods, once we tapped into color, it didn't improve performance.
Yeah.
And then there's a trade-off, right? Resolution versus color, etc. Right? So bandwidths, these are all factors that play into the design of hardware choices.
Yeah, thanks. We have the last question from Adam. So do you want to ask you, because it's quite long, that maybe
I can speak it more succinctly, and that is when you mentioned that cameras do work at night. It's true, but wouldn't we also need to define requirements or some standard for light sensitivity and other parameters, for example, aperture, to produce and reproduce fused results that would be considered safe? Because I'm assuming when that was said, it was considering fusion of the data with the a priori point cloud that the system was using to predict its state while it was driving. Over.
Mm-hmm. So that's a good question. It almost sounds like you're with an automotive background, because certification is something that is very crucial in automotive. You want to assure that the performance you demonstrate in one scenario, that it actually quantifies or carries over with this ideally same precision into all of these scenarios. I'm not saying that at night the system works the same with the same precision, definitely not. But we can also do localization with these stereo inertial RTK GPS fused systems in nighttime. So not just relocalization, but also localization. We demonstrated this in lots of demo drives. It works. I think the drift is slightly larger. I think Artisans has the exact numbers on their spec sheets, but it does work at night. But I think, with us, deploying these data sets for the community to tap into, to try and evaluate their methods, it, I think, could spark more research into night vision and night, algorithms for night vision. I think this is important. For example, one of the key driving criteria for all of our SLAM methods, as I argued, is brightness consistency. Now, if you switch on your headlights, the world becomes bright, but not brightness consistent, because once you move around, obviously your lights move along with you, and so brightness is not preserved for a corresponding 3D point. The brightness changes with the illumination. So what you should really do is you should really dig into the details of your light system in the car and model the illumination, that cone of light, and how it moves and how that modulates the lighting in the world. I don't think anyone has really done that yet. So this is the kinds of things that we would need to do to improve the precision in night scenarios, right? Just one example of things, challenges that are looming there for the vision community to tackle. And I think our data sets offer the possibility to look into these challenges.